I love the idea that in mathematics we have the word discriminant. It sounds almost like a discriminate, and I'm really not sure we should be discriminating against letters and numbers because it's not fair. And the age of discrimination is over. Anyway, quadratics, what is the discriminant? Our video for today. By the end of this video, we will hopefully cover the quadratic form, the intercept form, and the obvious word of discriminant. In a previous video, we looked at the turning point form or completing the square form, and we decided that that had a general idea that you had y equals x plus 1 squared minus 3. That allowed us to say, well, all right, that's great, that's a standard quadratic which has been moved 1 unit to the left and 3 units down, and we could draw a sketch and we could put the crossing points in and we can find bits and pieces, and life got very exciting and we realized it moved around. And if we had, for example, y equals 3x plus 2 squared minus 2,463, it looked like, an x graph that was 2 units that way and 2,463 units down, and it was squidged or stretched away from the x-axis by a factor of 3, and, the excitement was overwhelming and parties were had and everyone went mad around the world. Or not, as the case may be. So what does this have to do with our proverbial price of fish? Sometimes it's useful, and I said in a previous video, about finding out where a graph, or more specifically a quadratic, crosses the x-axis. When we drew graphs previously, we were very lucky because we could find the minimum point and we could find the crossing point on the y-axis, but I did make reference in our last video about, what about these points that cross? Let's recap. Here's an example of a graph that is a quadratic. We can see that because it's a U shape, or we'll assume it's a quadratic, and we have various points in the graph that were quite important to us. So we have this point here we know is our minimum, and we know that this point here is our y-axis intercept. But what about this point here and this point here, our x-axis intercepts? They're actually quite important too, and in an exam you would be expected, where a graph crosses, to be able to find those. And that's the next video in this series. However, do all graphs cross? Well, this graph here doesn't seem to actually cross the x-axis. It just seems to touch it, and that's quite important to us, right? The fact is that this graph here just touches the x-axis. It still has an intercept, and we'll use that word a bit more in a moment. It still has an intercept, but it doesn't seem to cross twice. There's one other example, and that's this graph here. Let's clear away the last two, just so we can get a better idea. What you may notice about this particular graph is it doesn't actually cross at all. This particular graph doesn't cross. Is there an easy way for us to try and find out whether a graph crosses twice, touches the x-axis in just one place, or in fact doesn't cross at all? Yep, it actually happens that there is. And this is what the focus of the video is called the discriminant. In the previous video, we came up with the idea that a quadratic could be written as y equals x squared plus 4x minus 6. It had a floaty 2, we had an x and a number. Now this isn't by any means just the be-all and end-all of quadratics. There are 4 different types that will try and trick you, and I will do that again in a much later video. But just let's get the idea now. Well, we could complete the square for this example, and we know how to do that. We put the x, we half this middle value and it becomes plus 2, and write the squared. And 2 squared is 4. We want minus 6. How to go from 4 to minus 6? I take away 10. And yay, these two versions here are really important to us because it means now that I have got my intercept. I know that that value there is my y-intercept, which is really important to me. And I know that now my turning point, or in fact I can go further and say my minimum, is given as minus 2 minus 10. That's really good. But writing a quadratic in this form actually helps us do something else. And this helps us to find whether a graph has 1, 2, or no crossing points at all. There's no point trying to find crossing points of axes if it doesn't actually have any. So normally we do a little bit of a test. We've got y equals ax squared plus bx plus c. Y equals ax squared plus bx plus c. If we look at our equation above, where we had y equals x squared plus 4x minus 6. We can now compare and find some rather interesting things. Well, firstly, what is the value in front of the x squared? Well, it says it's a, and what's in front of our x squared? Now, you might think it's 0. It's really not. It's 1. So I'm going to write over here my value of a, according to this formula up here, is 1. What is my value of b? Well, my value of b is actually equal to 4. It's positive 4. That's quite important. And what is my value of c? Well, that highlights the example quite well. It's actually minus 6. So I know, using this formula here, I can find values of a, b, and c by just comparing what's in front of the x squared term, the x, and the constant term. How does that help us? Well, this is where we get exciting, because we come up with this thing called the discriminant. For information, the discriminant is equal to b squared minus 4ac. You're going to see that again later on, but just take it as fact at the moment that that's a test for how many crossing points a quadratic has. It's the value of b squared minus 4 times a times c. Well, let's try it with the example I've got on the board and see whether we actually can find out anything. Well, that will be, right, b was equal to 4, so 4 squared minus 4 dot for my times. A is 1 dot c, which is negative 6. And so we get 4 squared is 16. Minus 4 times 1 is minus 4. Times minus 6 is plus 24. And so that comes to 40. Now you might turn around and say, yay, it's 40, that's really important. How? Well, that's where we get on to the next section, because one more piece of learning that's quite important to us is actually not whether this is a specific value. I don't care that it's 40. The number 40 doesn't mean anything to me. It's actually a test. Right, so we now know that our discriminant, and I'm just going to write it as disc, is equal to b squared minus 4ac. What we actually discover when we draw these graphs, and we've got a couple of examples coming out later on, is that if the value of b squared minus 4ac is greater than 0, that's a number bigger than 0, then our quadratic has 2 intercepts on the x-axis. So it has 2 intercepts on the x-axis. If b squared minus 4ac is equal to 0, then what we know is it just touches. It has, well, we'll call it at the moment, a repeated root. All right, we'll call it a repeated root. All right, or it has, I'm going to use the term one intercept, but it never really feels right to say that. And there's only one more case left, that if b squared minus 4ac is less than 0, or a negative number, then what we end up with is no intercepts. All right, so once again, because this really does not want to do a 0, there we go, b squared minus 4ac. So if the number comes out to be positive, then it has 2 intercepts. If it's equal to 0, it has a repeated root, or it's 1 intercept, it just touches the x-axis at a point. And if it's negative or less than 0, it has no intercept. So if we go back to our example that we did just a moment ago, there we go. So because our discriminant, our value of b squared minus 4ac was 40, that actually tells us it's greater than 0. So this graph here would have 2 intercepts. Right, so that would have 2 intercepts. That's the theory done. Let's have a look at some questions. So here's question 1. Y equals x squared minus 6x plus 8, and all I really want to know is whether it has 1, 2, or no x-intercepts. That's it for this moment in time. How do we do that? We use the general idea that the discriminant is equal to b squared minus 4ac. And what's our values of a, b, and c? Well, let's write them down. Well, the number in front of the x squared is a. So again, in this case, a is 1. B, in this case, is negative 6. It's the value in front of the x. And c works out to be 8. plus 8. And we just substitute those in, right? So b squared, so minus 6, I'll put it in brackets to make sure that minus 4 times 1 times 8. And what happens here? Well, minus 6 squared is 36. Minus 4 times 1 is minus 4, times 8 is minus 32. And 36 minus 32 gives me the royal value of 4. Am I actually bothered in the value of 4? No, not really. I just need to know that that's positive, and because it's positive, I will have 2 intercepts. This doesn't help me find the value of the intercepts, by the way. All it tells me is that there's going to be 2. Because math being a big fat trick, you're going to end up being in a situation where they may later on trick you. What about this? Yep, y equals x squared minus 8x plus 16. Same thing. So we have our a value is equal to 1, our b value is equal to negative 8, and our c value is equal to 16. Okay, so let's see what's the value of b squared minus 4ac. Well, b is minus 8, so minus 8 squared minus 4 times 1 times 16. Ooh, big numbers. Well, minus 8 is 64, or when you square it, it is. And minus 4 times 16 is also 64. And so what do we get? We get our value of 0. Again, that's really important to us. If we get a value of 0, that tells us that the quadratic will just touch my x-axis in one place, or it will have repeated roots. So there we go. Therefore, repeated roots. And I'm just going to write repeated roots, or RR. Final question for this series, because there really isn't too much more to this, is y equals 2x squared minus 3x plus 4. Well, a is now equal to 2, b is equal to negative 3, and c is equal to 4. Let's write our formula. It's always good to write the formula just so we can substitute things in properly. B squared minus 4ac. So b squared is minus 3 squared minus 4 times 2 times 4. Pretty sure I can see where this is going. Minus 3 squared is 9. Minus 4 times 2 is 8. 8 times 4 is, or minus 8 times 4 is minus 32. And so we get the grand total of minus 23. Not interested in the actual number, but we are interested in the fact that it's less than 0. And so as a result, this quadratic equation here will not have any x-intercepts at all. Well, nice short video hopefully. Not too much about discriminants. Not too much to learn about discriminants. Just remember b squared minus 4ac. Hope this has been useful to you. We'll see you again in the next video.